Okay, so welcome to to our first webinar of the year. I'm going to be covering a topic that I call parallel computing concepts. Cindy is going to put a couple of links into the chat. The first one is location where we're going to have the PDFs for all of the presentations in this series, including today's talk. And then I also have a link to a GitHub repo that covers some of the examples that we're going to be going over. So today is going to be mostly lecture, just a little bit of hands-on at the end, but I think you're going to find the notebook very helpful. All right, so just a little bit about Complex. So this is a new program started late last year, funded by the National Science Foundation. So the idea behind Complex, or comprehensive learning for end users to effectively utilize cyber infrastructure, is that we want to cover the training that non-programmers will need in order to effectively use supercomputers. So we know that over the years, more and more of our user base is somebody who's using somebody else's application. But there's still a lot that you need to know about parallel computing. So today we're going to be starting off with parallel computing concepts. Other topics in the series are going to include Linux tools and bash scripting, security, batch computing, how to get help, data management, and interactive computing. So with that, I'm going to jump into my presentation, start off with a little bit of an introduction. We're then going to go over processes, threads, MPI, and OpenMP, hybrid applications, Amdahl's law, other limits on the scalability of your applications, running parallel applications, and doing what we call a scaling study, and where to go next for more information. So I'm going to say that the reason most of you are here is that your workloads have grown to the point where you can no longer run them on your local resources. So most of you have probably been doing computing on laptops and desktop systems up till now. But now just the amount of data, the length of the calculations, the size of the simulation has grown. So you may need to start using parallel computing and the types of resources that we provide here at the San Diego Supercomputer Center and other national centers. So this session is intended for, let's say, anyone who currently runs, plans to run, or is thinking about running applications on parallel computers, who writes proposals for computer time on campus clusters, nationally allocated systems, or other resources. If you purchase time on compute resources, say in the cloud, and you want to maximize the return on your investment. If you're considering purchasing hardware for your lab, or you're just simply curious about parallel computing. So all good reasons to be here. So we're going to talk a little bit about the motivation for doing parallel computing and this session in particular. So much of the training in parallel computing is targeted at people who write their own parallel application. And we've done this for many, many years. We focus on things like MPI, OpenMP, CUDA, profiling, applications, performance tuning, all very, very important topics. But if you're not actually writing your own code, if you're primarily using somebody else's application, you really don't need to know these topics. I mentioned them earlier. We are not going to go into any of the details of MPI, OpenMP, or CUDA, but just maybe touch on them briefly so that you know what they are. Now, because of the way computing training has been done for parallel computing, oftentimes the end users who are not developers rarely or never get a proper introduction to parallel computing concepts. So even if you don't write code, it's so important that you understand some of the basic principles so that you can make the most effective use of the valuable advanced cyber infrastructure. So just talking about a few of the myths surrounding parallel computing. And I've come across these many times. So first of all, there's this idea that parallel computing is for astrophysicists, engineers, climate modelers, others working in traditionally math-intensive fields. And I'm going to say that this might have been partially true decades ago. Today, nearly every field of research makes use of parallel computing. This includes the social sciences, life sciences, arts and humanities, and in addition to our traditional user base of physics, chemistry, engineering, material science. Another myth of parallel computing is that if we throw more hardware at a problem, it will automatically reduce the time to solution. And I think most of you probably know this already, but parallel computing is only going to help if you have an application that has been specifically written to take advantage of parallel hardware. And even if you do have a parallel code, there's an inherent limit on the scalability. One caveat, though, is that a high throughput computing workload can use parallel computing to run many single core or single GPU instances of an application. And this would give you essentially perfect scaling. And then finally, another myth is that you need to be a programmer or a software developer to make use of parallel computing. And as I mentioned in the beginning, most users of parallel computers nowadays are not programmers. Instead, they're using mature third-party software that had been developed elsewhere and made available to the community. So in a nutshell, many of you are going to be using somebody else's code. If you're doing climate and weather simulations, you're going to use codes like WRF that I show over on the left side of the slide. If you're doing molecular dynamics simulations, biological systems, you're going to be using Amber and GROMACS and NAMD and other programs. If you're doing phylogenetics, you're going to use codes like RAXML and Mr. Bayes to construct those phylogenetic trees. If you're doing electronic structure, you might be using CP2K or VASP or other applications. So there's a lot of mature software out there, and I have a feeling that the majority of you are going to be using somebody else's code. Just a very, very quick introduction to parallel computers. Multiple clusters in parallel computers consist of multiple compute nodes connected by a fast network. Each of the CPU nodes on most of these nationally allocated systems are going to contain two processors, each with multiple cores. The GPU nodes will typically contain 4 GPUs to node. So even if you are running within a single node, you can still take advantage of parallel computing. So to effectively use this hardware, we need applications that have been parallelized so that they can run on multiple cores or multiple GPUs within a node or across multiple nodes. So Cindy, do we have any questions so far?
None at this time.
All right. I didn't think we would at this point. Okay, so now I'm going to talk about a few of the important concepts in parallel computing. We're going to talk about processes and threads, along with MPI and OpenMP. So you might have come across the terms processes and threads. These are both independent sequences of execution. You could think of a process as being an instance of a program with access to its own memory, state, and file descriptors. Basically means that a process can open and close files. Threads are lightweight entities that execute inside a process. Every process is going to have at least one thread, and threads within a process can access shared memory. Now, if you hunt online for resources describing the difference between threads and processes, most of them tend to be geared toward computer scientists. They get really deep in the weeds, but I found a couple of links here that I think do a reasonably good job of addressing the topic. There's one discussion here on Stack Overflow, which isn't too technical, but maybe a little on the nerdier side. And then at the bottom of the link to a article at educba.com, which is a little more informal. So the reason that we care about processes and threads is it's going to have an impact on how we run our applications. So a process, it's going to incur more overhead, but it's also more flexible. Multiple processes can be run within a compute node or across multiple compute nodes, what we call distributed memory parallel computing. Threads, on the other hand, they incur less overhead. Threaded codes can use less memory since threads within a process can have access to the same data structure. The downside, though, is that they're less flexible. Multiple threads associated with the process can only be run within a single compute node, which where all the processors have access to a shared pool of memory. All right, so why do you care? The type of parallelization in the application is going to determine where and how you can run your code. So distributed memory applications, multiple processors or multiple instances of the program, these can be run on one or more nodes. Shared memory applications, threaded applications, should be run on a single node. Now, we also have what we call hybrid applications, which are a mix of distributed memory and shared memory parallelization. They can be run on one or more nodes, but you need to consider the balance between threads and processes. And these hybrid applications are becoming much, much more common, especially as the number of CPUs on a processor has grown. And in all cases, you may need to think about how processes and threads are mapped and bound to cores. So in addition, being aware of threads and processes will help you to understand how your code is utilized in the hardware and identify some common problems. So I'm going to talk just a little bit about MPI. I know I said earlier that we're not going to cover programming topics, and we're not going to get into the details of MPI, but you should be aware of what it is. MPI is the standard for parallelizing C, C++, and Fortran codes so that they can run on distributed memory, multiple compute node systems. So while it's not officially adopted by any major standards bodies, it's really become the de facto standard, i.e. it's available almost everywhere, and almost everyone who does large-scale parallel computing uses it. Now, there are multiple open source implementations, including OpenMPI, MVAPIC, and MPIC, along with vendor-supported versions. MPI applications can be run within a single node, and all widely used MPI implementations are optimized to take advantage of the fast intranode communication. So basically, this means you can use MPI, you can have multiple processes running within a single node, but you won't personally need to worry about the details of how that communication within a node is implemented. MPI is portable. It could be used anywhere where an MPI library has been installed. And finally, though, although MPI is often synonymous with distributed memory parallelization, there are some other options that are gaining adoption, such as Charm++, UPC, and X10. So, although we're discussing MPI, the same principles are going to apply when parallelizing deep learning applications, say using Horovod, which is a distributed deep learning framework for TensorFlow, Keras, PyTorch, and Apache MXNet, and Nickel. This is the NVIDIA collective communication library. So a brief example of a code that's parallelized using MPI. If you don't have any programming experience, you don't really need to worry about these slides. If you've done a little bit of programming, you might want to follow along. So we're going to start off with the first program that you learn in just about any programming language, Hello World. So we show here on the left a C program implementing Hello World. Now, MPI applications are pretty dense. They're written at a low level. If I wanted to parallelize this, I'm going from the simple code to a parallel version. You're going to see that there's a lot more code in there. I've highlighted the new code in purple. This includes the MPI header, a bunch of calls to initialize the MPI environment, get the number of processes, get a rank or a number associated with each process, get the names of the processors, and then finally, I'm going to have each process write out its ID. So if you're not a programmer, application developer, you do not need to know MPI. You just need to be aware that it exists, and that if you're building your own executable, you'll need to use the appropriate wrappers. Okay, OpenMP is an application programming interface, API, for shared memory programming. Also in C, C++, and Fortran. OpenMP takes a little bit different approach. It gives a collection of compiler directives, library routines, and environment variables. It's actually implemented by the compiler rather than as a separate library. And to the best of my knowledge, OpenMP is supported by all of the major compilers, the IBM, Intel, GCC, PGI, the AMD optimizing compilers that we have installed in Expanse, AOCC. Like MPI, it's portable and can be used anywhere. And although OpenMP is often synonymous with shared memory parallelization, there are other options like Silk, POSIX threads, and specialized libraries for Python, R, and other languages. And then to show an example, again, if you're not a programmer, feel free to daydream for the next minute. But if you've done a little bit of programming, we'll show an example here of how code is parallelized using OpenMP. Again, you do not need to, if you're not a programmer or developer, you don't need to know OpenMP. You just need to be aware that it exists. And that if you're building your own executable, if you're getting the code from somebody else and you're actually building it on your system, then you're going to have to use the appropriate compiler flags. So what code that's been parallelized using OpenMP will look like is we might have a few definitions at the top, an OpenMP header. We might define the chunk size, the number of iterations of a loop that are going to be assigned to each thread. And then the individual loops are going to be parallelized using pragmas. We can do more complex parallelization. We can do task-based parallelization. We can organize the code into chunks. But mostly, we're going to be starting with our original code, and we're going to be adding these directives to do the parallelization. So let me just go over one more slide, and then we'll pause and see if there are any questions. So MPI and OpenMP, the big picture. On the left, we have processes. Again, multiple instances of a program that are communicating with each other. These multiple processes are managed using MPI, and MPI is implemented in libraries, such as mpitch, mvapitch, OpenMP, and vendor implementations. And on the right, we have threads, and multiple threads are managed using OpenMP, and OpenMP is implemented by the compilers, including GCC, PGI, Intel, and AOCC. And with that, I'm going to pause. And Cindy, do we have any questions?
Yes, we do have a couple.
Okay.
So one in the very beginning of this session was, I feel very tough to use parallel computing when it comes to post-processing and visualization. Any guidance?
Oh, so for so I see there's a little bit of discussion here. The parallel visualization is tough. I know that there are some tools that have come out of the national labs that allow you to do visualization in parallel. I'm not personally familiar with them. With post-processing, again, that's going to depend on what exactly it is that you're doing. You might want to see if there are any parallel implementations of what you're trying to do, or you may want to consider taking sort of a high throughput approach, where if at all possible, if you could take the output, and output could be processed independently. You could just do multiple instances of the post-processing. And then, Cindy, Cindy, I've got the chat open here.
So I have it listed, so I'll just kind of read through them.
Okay.
The next one is going to be, does distributed memory necessarily entail use of MPI?
Yes, that's a good question. I'm going to say 98% of the time, if you're doing distributed memory parallel computing, it's probably going to be MPI. I mentioned a few of the other options out there. Charm++, which is used in NAMD, a popular molecular dynamics code, but it's generally going to be MPI. Yep.
So next is going to be, do CPU cores have any relation to threads/processes? An example, if a CPU has 16 cores, does that mean it can support 16 processes?
Yeah, so there is a relation. Normally, you would do one thread. You would do one thread or one process per core. Now, if you experiment with some of the parallel codes, let's say that we have a CPU with 16 cores, you could actually run 32 threads across those 16 cores, but there's no free lunch. You're going to have threads or processes competing with each other. So ideally, you'll find that if you use more processes, say twice as many processes or threads as you do have cores, that they are going to only get 50% of that core.
All right, we have 4 more questions. Another one is MPI only for multiple processes on a single node, or can we use MPI for multiple nodes? If not, what can we use for using multiple processes on multiple nodes?
Yeah, so MPI can be used for both. The real power of MPI is that you can run across multiple nodes. And unless you're using Charm++ or some of the other options I described earlier, you will need to use MPI.
Next is parallel computing best with C, C++, and Fortran? Can OpenMP and MPI still be used with Python?
Okay, so the first question.
Is parallel
Yeah.
sorry.
Oh yeah, so yeah, Cindy, I got it. Thanks. So I'm gonna say it's a 3-way tie. We see a lot of parallel applications in C, in C++, and in Fortran. And ideally, it should work equally well. Now, can OpenMP and MPI still be used with Python? That's a little more complicated. Because of the way Python was designed, I believe that it cannot currently handle multiple threads. Now, regarding MPI, you can't use the MPI libraries as is, but there is a PyMPI implementation, which is very which closely follows the MPI standard.
A follow-up to that question is, what about Rust?
Rust, I'm completely unfamiliar with Rust. I did come across an article though where I think Rust does have some parallel computing capabilities built into the language from the start, but I don't know enough about that.
All right, just a couple more, Bob.
Okay.
Can we use MPI with R?
Okay, again, you won't be able to use you won't be able to use the MPI implementations that I mentioned earlier. But there is a yeah, I see Marty already addressed the using our MPI. But there are different libraries though for parallelizing R code.
All right, and then 2 more. Can you
Okay.
suggest profiling tools for analyzing performances of MPI, OpenMP, and CUDA-based programs applications?
Oh, okay. I didn't really want to get into profiling in this code since we're in this presentation, since we're not really covering programmer topics. I'm going to say if for serial codes, my favorite starting point is always gprof. For parallel codes, I'm going to say probably the state-of-the-art tool is something called Tau, which allows you to do a very detailed profiling of OpenMP and MPI applications.
Lastly, do we have any rule to decompose NOS or NOS of grids per processors for optimize resource allocations?
Okay, do we have any rule to decompose number of grids per? I'm going to say that there's not a hard and fast rule. I'm going to get into that a little bit later. I'm going to say, if I understand the question correctly, I would recommend that you actually want to benchmark your code and do a scaling study. So if your problem is too small, you won't be able to spread it across enough cores or nodes. So, and this is going to be the later part of the talk. I'm basically going to say do a benchmarking study.
And that is it for now, Bob. Thank you very
Okay,
much.
great. Thank you. And thank you, Marty and Cindy. Okay, so now we're going to move on. We're going to talk a little bit about hybrid applications. So many modern parallel applications, they're built using a hybrid approach. They take advantage of both distributed and shared memory. So this will typically involve MPI and OpenMP, although as I mentioned, some other combinations are possible. Now, hybrid codes have the advantage over purely shared and distributed memory apps, and that shared memory apps can have a limited scalability within the node and can definitely not be run across multiple nodes. Distributed memory apps may have a higher memory requirements and more overhead when running within a node. So we're going to take a look at a very, very simplified version of parallel computer. It just consists of two nodes, each of them with 16 compute cores. So the big gray box is going to be our node. Each of those little blue boxes will be a core, and we have a interconnect. So if we're running purely message passing application, they're typically going to be executed with one process per core. Again, we answered a question earlier. There's no hard and fast rule that says you can only run one process per core. But if you run multiple processes per core, they're going to be competing with each other, and your code's not going to run any faster. So here we see an example of an application running 32 processes across two 16-core nodes, and we have one process associated with each core. Now, if we have a threaded application, here we're just going to have a single process, and within that process, we're going to have multiple threads. So here we're showing an example of threaded application, single process running 16 threads across 16 cores. I said here that applications that are parallelized using threading only are restricted to running within a single node. For those of you who are sticklers for parallel computing, technically any programming model can be mapped to any hardware, but in practice, if you try to run an application with multiple threads across multiple nodes, you're going to get terrible performance. Now, hybrid applications is where we mix processes and threads. And this is going to be really, really important for a lot of you who are using existing third-party parallel applications. So any combination of threads and processes within a node is allowed. So here we see an example where we have two processes per node, those larger orange rectangles. But we have 16 threads, and we have 8 threads within each process. So again, we're still executing one thread per core, but we divide it up a little bit differently. So here we have 4 processes, 2 processes per node, and 8 threads per process. A typical scenario, and I'm going to say this is getting a little out of date, is to run one process per node and use threads within a node. But this is becoming a little less common as the number of cores on a node continues to grow. For hybrid apps, we need to try to choose the balance between processes and threads, given the range of options. So we show here on the left, one process per node, 16 threads per process, all the way down to, on the right, to one process per core. And the common question would be, how do I choose? And I'm going to say the only way to do this is that you'll need to benchmark your application. Try to run this with different combinations of processes and cores and see what gives you the best performance. So any questions before I move on to Amdahl's law?
Yes. Does a task in Slurm correspond to a process?
Ooh. Yes. Typically, a task will be associated with a process.
That is all, Bob.
Okay. All right. So now we're going to get on to Amdahl's law. We're going to get into a little more practical content. So if you know only one bit of theoretical parallel computing, it should be Amdahl's law. And this is a description of the absolute limit on the speed up of a code as a function of the proportion of the code that can be parallelized and the number of processes. So this is truly the most fundamental law of parallel computing. Right now, this is going to be a little abstract, but we're gonna say that P is the fraction of the code that can be parallelized. And it's a little hard to tell sometimes, what part of the code can be parallelized, but let's just assume for now that we can look at the entire workload for the application and say that P is the fraction that we can then parallelize. S is going to be the fraction of the code that must be run sequentially. So S plus P is going to equal to 1. And N is the number of processors. So the speed up that you're going to get as a function of the number of processors is going to be 1 over 1 minus P plus P over N. So you can see that the parallel part of the code, it's going to continue to, the time that we spend executing that is going to decrease with the number of processors. But the serial content, the time that we spend on that is going to be fixed. So in the limit, as the number of processes go to infinity, the theoretical speedup is going to depend only on the proportion of the parallel content. So we let n go to infinity. Our expression simplifies to 1 over 1 minus p, or 1 over s. So I'm going to say this doesn't look so bad, but we're going to show in the next slide that it doesn't take much serial content to impact the speedup of your code. So what I'm showing here is a plot. On the y-axis is the speedup, how much faster the code is running. And on the x-axis, I'm showing the number of cores. And this is a log scale at the bottom. So you can see that if the fraction of the code that could be parallelized is 50%, the maximum speedup, no matter how many processes we use, is only going to be 2. When we go to 75%, max speedup will be 4, 90% 10, 95% 20. So let's go a little bit further. Look at a code that has 99% parallel content. So even with 99% parallelizable content, we wouldn't even be able to make good use of a single modern 128 core node. So in this case, if we were running this code with P equals 99%, if we were here, indicated by the arrow, running on 128 cores, we would have only gotten a speed up of 60 instead of a speed up of 128. If you were running at this parallel efficiency on our supercomputers, we would be upset because you would be making bad use of the supercomputer, and you would be burning through your allocation much more quickly than you need to. So in addition to Amdahl's law, there are other limits on scalability. So as I mentioned, Amdahl's law, you know what, I'm going to pause here. Cindy, do we have more questions?
Yes, but Marty's kind of having the conversation through the chat. So
okay,
I'll let him complete that. We'll come back if they're still standing.
Okay, sounds good. All right, so Amdahl's law, this sets a theoretical upper limit on the speedup, but there are other things that are going to affect your scalability. There's going to be limits due to the problem size. There's communications overhead. There's going to be uneven load balancing. So in real life applications that involve communications and synchronization, for example, all the threads or processes must complete their work before proceeding, or irregular problems on non-Cartesian grids, the speedup can be much less than predicted by Amdahl's law. So I'm starting off with problem size limitations. And the only reason that I'm using Hello Kitty with a paintbrush in this example is that it was the only public domain image with a transparent background of a character with a paintbrush that I could find. And this is a really common example in introduction to parallel computing. So let's say that we have one person, or in this case, one kitty, is painting a fence. And we'll assume that it takes 48 minutes for the one kitty to paint the entire fence. And you would think intuitively that if we get 2 cats, that they would be able to paint the fence in half the time, or in 24 minutes. And then we might think if we use 4 cats, we could paint the fence in a quarter of the time, or in this case, 12 minutes, and maybe 8 cats that we could paint the fence in 16 minutes. And you can see now, the fence is getting a little crowded. There's really not enough work for each of the painters to do. And if we go to a ridiculous example, let's say that we had 32 painters trying to paint this fence. We see that there's just not enough work. So eventually, you're going to get to the point where there's not enough work to keep all of your processors or GPUs busy. And in fact, not only will the runtime level off, but you may see that your application runs slower since the parallel overhead associated with running on that many that many cores overwhelms the runtime. Another thing that can impact is what we call uneven load balancing. So parallelism code requires dividing the computational work into chunks that can be executed independently. Now, if the work cannot be distributed evenly, then processes are going to sit idle, waiting for that longest chunk to finish. So here's an example where, let's say we have 4 chunks of work, indicated by the solid blue boxes. These need to be completed before the next 4 chunks of work are done. So let's say that we assign these to CPUs 0, 1, 2, and 3. And the vertical bars are synchronization points where all of the tasks or the threads have to complete before proceeding. So for example, maybe the processes need to exchange newly computed results, or threads need to finish updating a shared array. So what's going to happen is CPU 1 is going to finish first, and then it's going to sit idle, followed by CPU 3 and CPU 0. So they're going to be sitting idle. They're not going to be doing any useful work while they're waiting for CPU 2 to finish. Then we assign the next 4 chunks of work. That this time CPU 1 got the longest chunk. CPUs 0, 1, and 3 are going to be waiting until CPU 1 finishes. So this is another factor that's going to affect our affect the speed up that we can get as we run in parallel. And then finally, there's communications overhead. This is really common if you're doing computational fluid dynamics or magnetohydrodynamics, climate, weather, any kind of simulation that involves solving systems of partial differential equations on a grid. I saw earlier in the chat somebody mentioned OpenFOAM. Yes, you can run OpenFOAM on our supercomputers, but when you run it, you're going to run into the situation that we're seeing here. So, but let's say we take our computational grid. Of course, this is a very, very, very small example. A 16 by 16 grid. We're going to divide this into 4 8 by 8 chunks, and we're going to distribute this across the 4 processes. Now we're going to assume that each cell is updated using the values of the 4 neighboring cells. So for the cells that are within the interior of each chunk, calculations can be done within each process. But you see, it's going to get a little more complicated for those cells that are at the boundaries. They're going to need data belonging to a neighboring process. So to accommodate this, typically the solutions of systems of partial differential equations will set up a halo of ghost cells around the grid. So we're going to periodically communicate data between these processes to fill these ghost cells, so that each cell along the boundary will have access to the data that it needs. So this data movement, this is going to introduce overhead. We're going to be limited both by the latency, how long it takes to communicate that first byte of data, and by the bandwidth, the rate at which we can move the data. So this is going to further impact the performance of a parallel application. So at this point, you might be thinking, how does anybody do parallel computing? We're limited by Amdahl's law, and then we have all of these other factors, related to problem size and communications overhead and load balancing. How does anybody ever use all the cores on a single modern compute node, let alone the full power of a large supercomputer? So first of all, the reality is that most parallel applications do not scale to thousands or even hundreds of cores. In fact, if you would look at the workload on Expanse, many of them run within a single node. So just because we have a supercomputer with tens of thousands or hundreds of thousands of cores doesn't mean that you need to use all of them. Also, there are strategies to achieve high scalability. We grow the problem size with the number of cores or nodes that we're using. We overlap the communication with the computation. We use dynamic load balancing to assign work to cores that become idle, or we increase the ratio of the computation and the communications. Again, this is all going to be done by the software developer. So within chemistry and molecular dynamics and fluid dynamics codes, the developers will have thought of these things so that they could get better performance. So I'm going to pause here and see if there are any questions.
Yes, we do have one or two. One is a true or false. In
Okay.
general, Slurm job array makes more efficient use of resources, open parenthesis, capable of freeing them up sooner, close parenthesis, than the same computational/parallel workload using GNU, parallel, open parenthesis, forces all processes and therefore resources to wait or idle until the last processes finishes.
Okay, so I am not familiar with GNU Parallel, but based on the description, I would say that Slurm job arrays would make more efficient use, because once one of those jobs within the array finishes, the hardware is then freed up and available for the next job.
Thank you, Bob. And then the last one is going to be, can you please clarify intraband and interpool communication? Which one is better? Do we need to use both intra and interpool?
Ooh, I'm not sure what you mean by intraband and interpool. I'm going to assume that, but by intraband, you mean within a compute node, as opposed to across. Okay, yes, I see a note here from Marty. Yes, so if you mean intranode and internode, I'm going to say that the communications is going to be faster within a node, because we don't need to go out to the network, and the MPI libraries are designed in such a way that they can implement the communications faster within a node. But do we need to use both intra and interpool, or intra and internode? If you want to run across multiple compute nodes, if you really want to do parallel computing at large scale, you'll need to do both. Now, the good thing is that you don't need to worry about the details of, oh, this is the communication being done between processes within a single node or across nodes. The appropriate protocol would be used.
And then two just came in. What do you mean by communications in the previous slide? Example given, increased ratio of computation to communications.
Yeah, let me go back. Sorry, Cindy, could you repeat that again?
Yes, it's what do you mean by communications in the previous slide?
Okay, yes, yes. By communications, we mean but moving data from one process to the next. I mentioned earlier that processes, you could think of a process as being an instance of a program, and it has its own memory space. So when it needs data belonging to another process, that has to be explicitly communicated using a communications library like MPI. Okay, so I'm going to move on. Okay, so now I left off here. I said all is not lost. We can still do parallel computing and sometimes still scale to very large number of nodes or cores. So first of all, regarding problem size limitations, sure, if you start with a very small problem, you may not be able to run it across a large number of cores, but often we solve a larger problem. So again, getting back to the fence painting example, we're not going to use 32 cats to paint a small fence, but we might use them to paint a much larger fence. This is really common in parallel computing, where let's say we're doing a climate or a weather simulation. We'll use a larger grid with a finer grid space, with finer grid size, and now we have more work that can be distributed across multiple nodes or cores. We can also overlap the communications with the computation. Again, this is something that's going to be implemented by the developer of the code, but I'm going to say that most well-written modern applications will do this, especially especially those that are solving systems of partial differential equations. So what we could do is we could be doing calculations on what we consider the interior cells while we're waiting for the communications to finish. So now there's going to be, while that data is being communicated, we're doing these other computations. We can do dynamic load balancing. Again, this is something that's going to be done by the developer of the code. So imagine that we have a set of tasks that could all be performed independently and they take varying amounts of time. So if we do a static assignment of those tasks to processors, that can lead to a large load imbalance. We can get better performance if we dynamically assign work to processors to become idle. So let's assume that we had 8 tasks that we need to complete. A, B, C, D, E, F, G, H. If we just took those first 4 tasks and assigned them to processor 0, and the last 4 tasks, processor 1, you can see that processor 1 is going to be finishing very early and waiting for processor 0 to finish its work. What we could do instead, what we call dynamic load balancing, is we can assign these tasks to processes as they become idle. So we might assign task A to processor 0, task B to processor 1. Processor 0 finishes its task, and then it gets C and D and E before P1 finishes B. Then we assign F to P1, G to P0, and then finally H to P1. So if we do this, if we assign the work as those processes become idle, we can greatly reduce the amount of wasted compute cycles. And then finally, let me stop here, and I'm going to get into what is probably the most practical part of this webinar. So, yeah, from what I could tell, it looks like okay, yeah, it looks like those have been answered already. So now I'm going to get into what I think is the probably most important practical thing that you need to know. So, and this is running parallel applications. So we talked about the basics of parallel computing, hardware and threads and processes and hybrid applications and Amdahl's law and other factors that affect scalability. So this is all, a lot of this is very theoretical. It's a lot of background, but how do we actually know how many CPUs or GPUs to use when running our parallel application? And the only way to definitively answer this question is to perform what we call a scaling study, where a representative problem is run on a different number of processors. And when I say representative, I mean one with the same size, say the grid dimensions, number of particles, number of images, number of genomes, and complexity, the level of theory, the type of analysis, the physics, as the research problem that you want to solve. So we see this a lot in requests for compute time, where the runtime as a function of the number of cores is shown using linear axes. So believe it or not, these two codes, the one on the left and the one on the right, have very, very different scaling behavior. But it's really hard to tell because when I look at this plot, the timings at large core counts are indistinguishable. And by large core counts, this isn't even that large. I just went up to 128 cores, the number of cores that we have on a single compute node of expense. So the right way to plot the scaling data is to use log axes. So notice these are, I'm plotting the same data that I showed in the previous slide, exact same data, except now we're using log axes. So we can see the code on the left. This is an example of a code that has perfect scalability. As we increase the number of cores, the parallel efficiency stays at 1, and the runtime decreases proportionally to the number of cores. If we look on the right, we could see that in the beginning, we're doing pretty well. We're getting good performance, but the parallel efficiency, the speed up divided by the number of cores, it really drops off. Okay, let me, all right. So where should you be on the scaling curve? So I'm going to say if your work is not particularly sensitive to the time to complete a single run, consider using a CPU or a GPU count at or very close to 100% efficiency. Sometimes that may even mean running many jobs each on a single core. This makes sense for parameter sweep workloads where the same calculations run many times with different sets of inputs. So if you're doing, say, molecular dynamics or computational chemistry, and you need to do a large number of simulations, run each of those at a smaller CPU or a GPU count where you're getting close to linear speedup. Now, sometimes you can go a little bit further out on the scaling curve if the job would take an unreasonably long time to finish at lower core counts, or if a shorter time to solution helps you make progress in your research. Now, if your code doesn't have checkpoint restart capabilities and the runtime would exceed queue limits, you might have no choice but to run at a higher core count. Sometimes you're going to be doing computing where the time to solution is critical. This might be a little more common using hardware that you have in your own lab. So for example, if you have calculations that need to run on a regular schedule, data collected during the day has to be processed overnight, or if you're doing severe weather forecasting. I should mention, though, that you shouldn't be doing severe weather forecasting on our supercomputers. They're not designed for operational work. So, for example, if we need to use more cores in order to finish processing the data overnight, or doing, again, if you're doing operational work, not necessarily in our supercomputers, as long as the code was running faster, you'd probably sacrifice some parallel efficiency for the sake of getting that result quickly. I know I'm going to skip over that, and I'm just going to go to the go to the questions.
Oh, okay. Sorry, I'm trying to, let's see, where do we stop at? Okay.
Yep.
One is there any difference between using tensors or matrices or vectors in Python in order to better parallelize the code? How to find out S and P in the mentioned law?
Okay. So is there any difference between tensors or matrices or vectors? It depends on the type of the calculation that you're doing. If you're, say, working with PyTorch, you do want to be working with tensors. As far as matrices versus vectors, I would say if you're using NumPy arrays, that would probably be better than native Python vectors. Okay, and now how to find S and P in the mentioned law? There's really no easy way to do that. In some simple codes, you might be able to look at the calculations, figure out that there's something like maybe IO or initialization that has to be done serially, and try timing that portion of the code, and then looking at another portion of the code where it's potentially parallelizable. Generally, we don't know exactly what S and P are. And your best option is just to do a benchmarking study of your code. And then I see Marty already answered the question about running 2 or more processes per node. Okay, and then from Shashi Mishra, when writing parallel code, dynamic allocation versus static. Yep, so Marty covered that already. And again, we're not covering programmer topics here, but it's going to depend on your it's going to depend on your application. If say the amount of work being done per iteration is uniform, you probably want to do static. But if you have an application where, say, there could be a large variation in work done per iteration, you might want to go dynamic. And I've worked on codes where I've done both. Okay, so we are just here at the end of the hour. Where to go next in conclusions? So we just scratched the surface. There's a link here to our training catalog. And also, if you're familiar with the Access program, the Fall I Want to Exceed, they'll soon be implementing a training catalog. You can also find examples of user guides for the NSF allocated resources at these following links. So just to wrap up, parallel computing is for everyone who wants to accomplish more research and solve more challenging problems. You don't need to be a programmer, but you do need to know some of the fundamentals in order to effectively use parallel computers. Remember, processes, it could be thought of as instances of a program. Threads run within a process and access shared data. MPI and OpenMP are both used to parallelize code. Amdahl's law gives you a strict upper limit in scalability, but there are going to be other factors that affect your scalability. And then finally, know how to display your scaling data and choose core counts. And with that, I'm going to stop sharing. I'm going to go over to my GitHub repo. Let me just check the yeah, so I see the question about parallel efficiency has been addressed already. Yeah, so basically it's the speed up divided by the number of processes or threads. And then finally, Carl asked, can you comment on which or some of the more frequent applications use hybrid MPI and OpenMP? Oh, can you comment? Carl, I'll have to get back to you on that question. I know though that most of the widely used parallel applications that run across multiple nodes do use MPI plus OpenMP. And Marty addressed the question about when you said tensors are better. Yeah, so tensors, yeah. So I would use tensors specifically if you have deep learning workloads. And for those of you who are going to stick around, I'm going to give a quick demo of the code that we have for generating and scaling plots. So as Cindy mentioned, yes, Elliot, is it possible to get a copy of the slides? Yes, we had posted them earlier. Cindy, if you can go ahead and paste the link in again, that would be great.
You got it. I'll take care of that.
All right. Question here from Rena. And again, as Cindy mentioned earlier, we are done with the official presentation, but I will be sticking around for the next half hour to do a little demo and answer questions. From Rena, regarding the scaling curve, why do we care about parallel efficiency? In theory, increased efficiency is nice, but that's a trade-off. What are the practical reasons we care about efficiency? Yes, that's a great question. Particularly with our supercomputers that are allocated, allocated through through Access and available to the entire research community. We want to make sure that they're being used efficiently. So, for example, if you were running an application that's only getting 50%, that's only getting 50% parallel efficiency, you're essentially wasting half of those resources that could be used for another calculation. And I see that David Landay also weighed in. You might care if you had to pay money for the resources used. Exactly. If you're doing cloud computing, and those cloud computing resources were coming out of your research budget, you'd be spending more money than you need to. So one way or the other, either you're wasting a shared resource like like Expanse and Bridges and Stampede 3, or you're wasting money on cloud resources. All right, I don't see any other questions that we haven't addressed. Although I do want to follow up on a comment here from Ulf Schiller, also requesting fewer resources may reduce the wait time in the queue. Yeah, that is correct. It's going to depend on the scheduling policies for that particular machine. If you're running at very large scale and say using Stampede 3 or the large systems at the national labs, they may have scheduling policies that make it a little more favorable for the very large jobs. But generally, though, requesting fewer resources can reduce your wait time in the queue. Okay, and then question here from Ava Spangler. What sort of error might you see if you have too many workers and not enough work? Yeah, and I think David's answer there is good. You probably won't see an error. You're just going to see a performance hit. So in fact, I don't think I've ever come across an example where I've run on too many cores or too many nodes and got incorrect answers. Now let me go over to the GitHub repo for those of you who are still here. Okay, so earlier, Cindy had posted a link to the GitHub repo that we use today. So if you go here to my parallel computing concepts repo, you'll see that I have examples for Amdahl's law and strong scaling. So these were the Python notebooks that I used to generate the figures for this presentation. And down at the bottom, you'll also see that there is that you can launch these using Binder. So I had done that earlier, and unless my code, let me restart here. We'll go to the Amdahl's law example first. No, I think my session must have expired. I started that too early. Let me try launching that again. Let me go back to Amdahl's law. Okay. Okay, so if you want to play around with Amdahl's law, you can open this notebook. I use matplotlib to generate the figures. I have some data sets showing speed up with 50%, 75, 90, 95, and 99% parallel content. Oop, sorry, I need to. And if you want, you can experiment with this. Let me add would add another line here for 99.9% parallel content. And I think what you're going to find even more useful, though, is the notebook for the strong scaling. Oh, let me go. Looking at questions here. Okay, looks like that's been addressed already. But in the strong scaling example, we can use this to generate scaling plots that you can use in your allocation requests. So I have all the code here for doing the plotting the scaling data on linear axes and on log axes. And you can actually use this to generate generate scaling examples that are pretty much ready to go. Now I realize that I didn't update the binder image. I will do that later. But if we actually go to the parallel computing concepts repo, that I have an example down at the bottom where you can enter your own information, your cores or GPUs, the runtime, the units, whether using CPUs or GPUs, time units, and so on, and generate scaling plots that are pretty much ready to go. Okay, so any questions?
We did get a question in the chat. Is there a way to calculate percentage parallelizable content, or is the visualization for Amdahl's law more of a theoretical concept?
Yeah, I'm going to say that it's more of a theoretical concept. So, Rena, I talked about that a little bit earlier. Unless you have a very, very simple application, and you manually put in timers around the serial and the parallel. Well, yeah, and put timers around the serial and potentially parallelizable content to determine how much time is being spent in each chunk. You probably won't be able to calculate PRS. It's really more of a theoretical concept. And the main purpose of Amdahl's law is to really drive home how little serial content you need to really limit your ability to run on a large number of cores or nodes. So again, I'm going to say the most important thing is to just be aware that we have be aware that Amdahl's law exists, that we do have those limits, but practically you'll want to generate scaling curves like I described in the presentation and the GitHub repo. All right, so we are now I guess we're kind of into the office hours part of the presentation. So Cindy, I'm going to say you could probably stop recording